welcome to week 5. So by this point, we've gone over all the CAD that we want you guys to know, and I feel like for the most part, you guys have a hang of it. And of course, we'll practice that a lot more as we get into these next couple of weeks. But before we do that, there's a couple of really important FRC specific stuff we have to go over. So that's what today will be. At the end.
So we're just going to go over a lot of the basic things that you need to know about the season and like inspiration from other robots. So first, the layout of the FRC season and some like classic FRC designs and things that you might need to know. Mechanisms for drivetrains, intakes, and arms and elevators.
So we've gone over this a couple times before, but we just want to make sure you guys are aware of this. In terms of what a year looks like for us, right now we're in the off season, which is from May to August. For us, that means training. So that's what we've been doing this past almost month. And just, really relaxed. It's not really stressful. And then once the school year starts and we start getting into the fall to winter season, it's preseason, so September to December. And there are a couple of practice competitions, and we still continue training, continue answering questions and talking about all the stuff we've been doing. And then the first Saturday of January is kickoff. They tell us a challenge, and then we start to brainstorm all our designs. And then build season is from January to February. It's a bit more flexible this year because there's no end to build season. We can keep building. However, we want to get our robot built as quickly as possible so we can test it and make sure everything works, which we haven't done before. We haven't finished it completely in time. And then from March to April is competitions, and we hopefully win. And we continue that every year.
Okay, so chassis and drivetrain is basically what you use to propel your robot around the field. So a couple of key factors that we look at when we're designing the chassis and the motors and gearboxes that go with it. Top speed. If you have like a wide open field, you want to be able to get around as quickly as possible. So yeah, acceleration. If the field is like more limited with like small stretches, you might want to look at like the length of the stretch and like the length that you want your cycle to be, and then you decide how much torque you want for your gearbox. Traction. If you anticipate that there's going to be a lot of defense in the game, you want to have wheels that will suit you for that, so you get like higher grippier wheels or things like that.
By defense, he means sometimes robots, to prevent you scoring, they will ram you and push you.
Yeah.
There are, of course, rules stopping like damage to the robot, but in general, robots can push you to stop you from scoring.
So you want to be able to push other people if necessary and not get pushed around too much. Then maneuverability. So if there's a lot of obstacles or like other robots on the field, you want to be able to get around them and not get hit. And it also helps with lining up the targets if you want to score quickly.
So in terms of wheels, there are tons of types of wheels out there. So what we have in the robot, what we've used previously for the most part, are the high grip wheels, which are these ones right here. And the diameter varies to 4 or 6 inches. But the important thing is at the outside there's a rubber tread. And it's really high grip. It's good for traction. Then there are Coulson wheels. They're generally smaller and have a lot of different width options. They're also fairly high traction. Pneumatic wheels, these ones right here. And they're what they sound like. They have air filled inside of them. And so chassis that have pneumatic wheels can withstand a really big bump because they can bounce a little bit. So depending on the challenge, you might want that. And then you can put whatever kind of tread you want in certain wheels, not only for your chassis, but for other stuff as well, depending on the surface.
So the first and most basic drivetrain that we're going to be looking at is the tank drive. So it kind of works with like the tank style of control where you have the left side working together and the right side working together. So one joystick will be paired to each of them. Usually the center wheel is dropped slightly more than the other two, so you don't have too much friction on the ground at one time and it helps with turning. There's another style of drive called the West Coast variation of the tank drive. It's what we normally use, where instead of having this side plate, it's just left open, so the axles are just put at the end. Sometimes, if the challenge requires it, we can put omni wheels on the ends, and that will allow you to turn a lot easier as you don't have as much friction from that side. And the advantages of this type of drivetrain are that it's very easy and common to build, and there's lots of resources for it. but the issue with it is it lacks maneuverability, as it's a lot harder to control for the driver.
So it's also pretty high traction depending on the wheels that you use. And what Ritwik said about the center wheels being lower. So center drop is pretty common. And the way it works, just real quick, if this is the side of your chassis, right? If you put your center wheel lower, and then these two outside wheels slightly higher, right? Whenever it turns, only the two wheels in the center are going to be touching the ground. And so that's what he means by it'll be easier to turn. It'll give you that slight maneuverability. And then these two wheels only engage forward and backward. So it's a way to kind of make tank drive a little bit more maneuverable.
Yeah.
So yeah.
And then you can configure tank drive with 2 wheels on each side up to 4 wheels on each side, depending on what you want.
So mechanism and holonomic drives. So these are pretty cool. So basically, the mechanism wheels over here, as you can see, they have 45-degree little like rotational wheel thingies.
These rollers. Right?
Yeah, they're called rollers, right? Good job. Basically, because they're at a 45-degree angle, you can, by using different combinations of them on each corner, you can make your robot move in a lot of directions. Essentially, you can keep your chassis oriented one way, and by turning your wheels forward and backward and side, you can get it to slide around.
Yeah, it can move and turn in any direction, and you can move while you're turning too, so you can do arcs and stuff around the field.
Yeah, so it's high maneuverability. The problem with mechanisms are that your chassis has to be really flat. It can't be slightly bent, which might happen as a result of the building process. We've tried it before. It's a bit difficult on our programmers as well. Holonomic drive, it's a similar idea, except instead of using mechanism wheels, which have the 45-degree angle, it uses omni wheels, which are basically the exact same thing, except that instead of being in a 45-degree angle, it's in line with the tread. It's just 2 sets of wheels following little rollers following the direction of the wheel, and it achieves the same effect, except it takes a little bit more internal space. So it's a bit easier to do than the mechanisms, I think. But
yeah, here all of the wheels are 90 degrees to each other.
Yeah.
So one in each corner.
So like we said before, high maneuverability, but they get pushed around really easily. So that's why we might not always want them, depending on the challenge. We have to really settle into a role if we wanted to use these.
And with Mecanum, if you're moving sideways, you're turning the wheels against each other, so you lose a lot of force to friction, and it's a lot slower. Oh, yeah. So swerve drive, some of you might have seen the modules earlier. So it has the ability to rotate the wheel 360 degrees while also spinning the wheel at the same time. So it gives you the same range of motion as the Mecanum wheels, except since the wheel is spinning to go with the direction that you want, it gives you full power in that direction, so you don't lose any traction or power. So you can play defense just like a tank drive, essentially, except still have the maneuverability of a Mecanum or holonomic. The issue with this is it's a lot more difficult to implement, a lot more complex, so we haven't really used it yet.
Yeah, we've tried to use it in one of our off-season competitions. That's one reason that the off-season competitions are really useful, is because there's no actual consequence to losing or winning or whatever. So we can really try out different concepts during them. And in this case, swerve drives are pretty expensive. And they're really difficult to implement, in terms of the coding and the building and all the design that has to go into them. But if a team makes a good swerve drive, it can really help them during the competition. And H drive, so we've talked about omni wheels before, and so essentially the reason it's called H drive, because if I have my chassis like this, right, there's a wheel here, wheel here, wheel here, wheel here, wheel here, wheel here, and then there's a wheel sideways in the middle. And so since omni wheels have rollers, right, they have rollers facing this way, right, into the direction of the wheel. Omni wheels have traction going forwards and backwards, but they have no traction side to side. So that's why we have the sideways wheel. That's also an omni wheel. So again, this wheel can move side to side, but it can't move forward and backwards. So that's why in this case, you can get away with this and have many angles covered. Downsides to this, I would say, are you lose a little bit of space with the middle wheel, but you do get a lot of traction, I mean, a lot of maneuverability with it. It's really easy to make, but you don't have high traction. So you'll be a pushover, literally, if you make this chassis.
And then there's a lot more exotic drivetrains that we can look into. So what these use are pistons, and they can push down this kind of like system that's set up here that has two wheels. So one wheel is usually like omni wheel or mechanism wheel, and the other one's traction. So it gives you the tank drive, but you can switch into like the omni or mechanism drive. With these wheels being pushed down, it lifts the rest of the robot up a little bit higher. So basically it gives you both the tank, and if you want to switch to the mechanism or omni, you can do that. The issues with it are it's really complex to implement, and there's a lot of extra weight that comes along with it.
Yeah, so if you see here, just looking at it, it's extremely bulky. So unless you need this for your strategy, we probably wouldn't do it. Just because we don't have that much experience with it as well.
And this one, it's the like traction tank drive plus the along with both of the ball shooters that we looked at before, we usually have some sort of ball storage method if we have like a lot of small game elements. So it's like a hopper that has all these plates alongside or along with the length of the robot, and this can fill up all the way with like wiffle balls or other small elements. So with the hopper, you want to guide, like you can't just, or you can have it gravity fed where all like the bottom slopes down to like one corner, and that's where the shooter is. So the shooter can pick up the balls from there. Or a lot of teams, they have like active methods to move them around and serialize them. So one way is where you have a series of belts that go along like the length of the base of the hopper, and that will pull the balls to one side. Or some teams, they have like a giant rotating arm, like sweeping arm around the base, and that'll pull it to like one side or one corner.
So one thing to keep in mind, right? So you can have a ball shooter, right? It's pretty easy to make, right? And you just get the wheels spinning and you feed the ball and you shoot it. But this is all about how do we get the balls to that place in the first place. So with a hopper design, just a passive hopper, by that we mean it just exists and funnels them into one place. The way you would get balls into this is usually from some sort of loading station. So games in the past, to put game pieces onto your robot, there's usually some sort of place where a human can put the pieces into the robot. Sometimes the balls fall to the ground, and this would not be a good design for that because of just the way it's designed.
But yeah, we'll get to that next.
Yeah. So if you want to pick up from the ground, because a lot of times the balls will fall onto the ground, you want to use some sort of roller intake. In terms of a horizontal bar, that would be this one. So as you can see, a bar is placed parallel to the ground, and it spins, and it's at the height of the top of the ball. So when any ball rolls into it, it just gets sucked into wherever you want it to go. And that could feed into some other system. A wide intake is really useful because you don't have to be that precise. So driving the robots isn't the easiest thing, especially if you can't see where it's going too well. So this intake is slightly wider than the ball, just so the driver can, be pretty confident in their driving. Side rollers, like this, for example, are useful for, they can be useful for balls, but they're also useful for larger things. If you want to pick up a single object at a time and raise it up high, then you would use something like that. And that's pretty versatile in terms of what you can use it for. And it's not the most difficult thing to build.
Yeah, so with both of these, you can also substitute, or you can just have like a plain bar that has like some sort of grip on it, so it'll just be like a PVC pipe or something like that. You can put compliant wheels on it. Those are the rubber wheels what we saw earlier that like grip the ball. Or you can use something like mechanism wheels, and that'll help you like center it to a specific point. A lot of teams, they use this in conjunction with this type of intake. So this will like suck it straight into the robot, and this will hold it to a specific position, and that'll help you with scoring. There's another variation of this called an over-the-bumper intake. So that will actually extend out of the robot, and we'll use the bumpers as like a back surface to pull the ball up. That helps with like saving space on the robot, as you can move like your holding mechanism further to the front and have the intake on the outside. Okay, so first, if you have like your ball or scoring element in place, you want to be able to move it to like say a higher position. You would use something like an elevator or an arm. So first is elevators. So basically, the goal of an elevator is to just raise a series of stages vertically in one axis. So they use a system of pulleys in either chain or some sort of cord. The cord that we probably use is like called dynamo cord. and those are rigged up in like a certain method that will allow the stages to move up together. So if you look at this like inner carriage would slide all the way up to here, and then this stage right here could slide along this bar up to that length as well.
So essentially, a real quick way of seeing how they sort of work. This bar is attached to the frame. It's going nowhere. This is the elevator frame, and if you have like if you have like a pulley system, right? You can tug on this pulley, and that'll raise the entire frame up or down. Essentially, that's all it is. And then it has little like rail slidey mounts that'll follow it to make sure it doesn't get out of the frame.
So one of the issues with elevators is that the stages can sometimes bind up because of like the weight and friction between the like bearings and the bars. So sometimes what we use is like a constant force spring. This is just like a piece of bent metal that will pull down with a certain force. So it'll oppose the force of gravity on the parts of the elevator and make it easier to lift up and down by the motor.
So yeah.
You can go.
So if you need to go really high up with an elevator, you can put elevators and elevators and elevators. You can have several stages on an elevator. The problem is, again, it's a lot of weight. So, and when your weight is limited to 120 pounds, if, for example, you're a team that made a 5-stage elevator last year, whose just the metal took up 50 pounds, that takes away a lot of what you can do with the rest of your robot. There was a team that built like a 4 or 5-stage elevator, and it worked, yeah, but it was really slow and it had some problems. So
when you're designing something like this, keep in mind where you need to score and just be like as conservative with your materials and weight as possible. With the elevators, there's one more thing that we might want to note. There's like 2 main types of rigging that will give you different motion for your stages. So first is continuous rigging. That'll just move, this stage will reach its top limit first, and then the next stage will start moving, so it's one at a time. There's and continuous rigging has the strain going from the motor all the way up and down until it gets to the very last stage, so that's a lot of strain when you're like extended to the full length. There's cascading rigging, so it has one continuous piece of length, or like piece of string for each stage. So it's a smaller piece of string that will actually be on the bobbin of the motor, and all the stages will move simultaneously, so it's a lot more predictable for what motion you're gonna have.
So you can either have all of your different stages hooked up with one rope, is what he's saying, with one cord, and that'll make them all go up, or you can just have a separate motor and cord for each stage. And so it just depends on what you want, what you need. And arms. So arms are an alternative to an elevator, depending on how you want to make it. And it can be made out of metal, polycarbonate, whatever. And so what that second bullet point means is that you can either have a single arm, or you can be clever with arms. So you can have one arm, and this arm can swing up or down or wherever, right? But if I have a mechanism attached on the end of this, the face of this will change to whatever angle the arm's at, right? If I have 2 arms, right, and I attach a plate to the end of this, and both of these could roll, and the whole thing goes up and down, which is what we did on a robot this past year. This end plate will stay in whatever angle you set it up in. So we set up ours to be perpendicular to the ground, so it would always face like this. And with 2 pairs of arms, you can achieve that. So this is called a 4-bar mechanism, because there are, from the top view, there's two bars per arm, and then there's 2 sets of this. And one of the advantages is it's like not hard to, you just have like a strong motor and an arm, and boom, you're done. But the thing is, the motor has to be strong. You're going to make your arm as light as possible, because the more weight you put on the end of the arm, the harder it is to control, the stronger your motor needs to be. And there are limits on all that. And yeah, so there are good sides and downsides. We went for it this last year because it was really simple to build, just a motor and the bars, but it had its own problems. And you can combine them with a single stage elevator, depending. You can have an elevator and a small arm on the elevator, or however you want, and you can combine a lot of these mechanisms together. So, I guess as homework, we will send out links on Slack for a bunch of robot reveals and sources where you guys can get inspiration for your own mechanisms. And just start thinking about this, because we don't want to just tell you guys, hey, if you had this challenge, what would you do, without at least getting some exposure to some previous challenges first. Basically what we're going to do, we're going to give you guys some challenges, nothing too complicated, and just throw out any ideas or discuss among yourselves what would you think of doing for this challenge. So, number 1, the challenge involves taking a large cube and being able to score it in several locations of varying height. So you have a cube like this, and then you have to put it on different platforms. Sure. And then the higher the platform, the more points you get. The more cubes per platform, the more points you get. Here, let's do this. Bottom one is 2 points, middle one is 4 points, top one is 12 points. What kind of chassis sort of thing, what kind of mechanism would you want to do? Oh, okay, let's give some heights. This is 0 feet. This is 3 feet. This is 6 feet. Anyone have any ideas? Here, let's just start this way. What kind of drivetrain system would you want to use? Is there any particular one? It's a flat field, 54 feet across, I think is the typical. 54 feet, and there is one of these racks on either side. This is the red side, this is the blue side.
The racks are like feeding stations. Right?
No, the racks are those.
Oh, where do they get the cubes?
They get the cubes at the loading stations. This is where you get the cubes. This is where you load the cubes. Right next to, and then your drivers are right here, in the center of each side. You can move if you're straining your neck. Okay. Do you guys feel like you would need to use, what kind of wheels or what kind of chassis would you want to use? Anyone, any ideas? So what we've said was you could use a tank drive, just a basic tank drive with high grip wheels, basically what we have on the robot now. That worked pretty well. What else? Well, what might work slightly better?
Or I guess let's think about the game a little bit too, based on the field.
Yeah.
It's a wide open field with no central obstacles, and the sides are like fairly open to each other. So if there's 3 robots on each side, and there's like 2 scoring locations, and there's like 1 free robot, then you might anticipate that the 3rd robot would play defense on your team.
Yeah. So that's one thing to consider, is that since the field is so open, right, like Ritwik said, it'll be easy for other teams to try to knock you off your game. Other teams can push into you and stop you from scoring.
And you have a wide open view from your driver's station all the way across the field, so you can see your robot no matter where it is.
So it's easy. It'd be easy to drive in this case, for example. Here, what are some other drivetrains that we've told you about? Let's go over them. The H. Okay. What is the H? What does the H drive do? It has omni wheels.
And you can go in any direction.
You can. So why would that be good or bad?
You wouldn't have to turn.
It's true. You wouldn't have to turn.
It would be easy to like knock you aside.
Exactly. So if you wanted to use an H drive, what else could you do to your robot? I'm trying to think outside the box. If it's easy to push you around, what might be one way to get around that? Yeah.
Make it heavy.
You can make your robot heavier than other robots. You can really go up to that weight limit, and that way it'll be harder for other people to push you around. It's good. So the thing is that sometimes people build the robots like really light, and then just literally just put blocks of aluminum or steel to make it the right weight, which might work. It all depends on your like weight distribution. Okay, so H drive, pros, cons, right? If you want to use it, you'd have to have a strategy for it. What are the drives you talk about?
The
Mechanical.
Yeah. So that one is
45.
yeah. So the wheels, the mechanical and the holonomic are basically the same, right? And again, similar to the H drive, like high mobility, low traction. So if you want to use those, you need a really sort of a good strategy, or you need a robot protecting you in that case. There's one design out here that's probably the best, but also the hardest. Why?
Oh, because you don't lose speed and you can still turn.
Yeah. So the turning on Swerve is ridiculous. It's like really good. But also, Swerve's drives don't lose. They don't lose traction. We can put whatever wheels we want on a Swerve drive. We can put, putting Omni wheels on a Swerve drive would be pointless. But you can put really high traction wheels on a Swerve drive, and they'd be pretty strong.
The point about power and speed is actually good too, because your motor is always pushing it 100% no matter what direction it's going at, or whatever you want it to. But if you have Mecanum, you're losing force because you have to spin the wheels against each other.
Yeah. So I don't know if you like. So what he means by that is that if I spin this one, each one of these rollers is going to want to go in this direction, right? If I spin this one, they're going to go in this direction. If I spin it this way, right? If I turn them this way. But if I turn both of them at the same time, the resulting vector is just straightforward. So that's what he means by you're going to lose some power with the mechanism if you want to go forward, whereas with a Swerve, you'll always go full power in each direction. Hi, Alex. Look, if you had this challenge, what would you do?
What is the challenge, sorry?
You have to put these 1-foot cubes onto a platform,
Okay.
and then there are 3 levels to that platform, and they give varying points. The field is wide open.
Mm-hmm. So what are your ideas so far?
We've talked about chassis.
Oh, chassis, okay.
Yeah. So now that we've gone through most of the options, individually, which one would you pick? Sweet. Swerve. Okay.
Swerve.
Either Swerve or that other one. I think it was called the Grasshopper or something.
Okay. So now let me tell you something else. Let's say in this challenge, your team has never used a Swerve drive before. What would you choose? Would you want to risk it and build your first Swerve drive on this one?
So I think you should also think about is that mobility actually needed, right? I mean, if you have platforms like this, okay, and you're trying to put a cube on, is it essential that the cube is necessarily, well, I don't know, in your challenge, does the cube have to be,
Nope.
it just has to
Yeah,
be
they're
on
like
it, right?
open on every
just has to
side.
be-
Large open platform.
Yeah, large open platform. You don't
So
have to be
you don't even
super
have to
precise with it.
turn that
So
much.
one thing to consider is that, like JP was saying, the Swerve drive is very complicated. It's really cool in practice, and actually, I don't know if you've seen the Swerve drive modules we
Yeah,
have. in,
I'll bring them out. I don't think everyone's seen them.
yeah.
But we
So the
should.
Swerve module is really, really cool, and if you can implement it, it's really, really neat. But a lot of times, it might not be worth the complexity sometimes. So I think one thing to kind of consider if you want a Swerve drive is like how precise do you have to be? Do you have to really line yourself up, right? Because if you're trying to line up with something and if you're off a little bit, then that's okay. Maybe the Swerve drive won't be necessary. But I think it's an interesting challenge.
Okay. So for intakes, let's assume that we're getting the cubes from the ground in like the back locations that you pointed out. So considering that we can use motors, pneumatics, actuators, and the things that we talked about before, what kind of intake or picking mechanisms would you use? Any ideas? Yeah, sure.
The thing with like the 2 wheels that like roll and then it like sucks in.
What kind of wheels would you use? And why?
Squishy rubber ones.
Compliant wheels.
Yeah. Okay. Any other ideas?
Thanks, right? Yeah. Here's the lesson out of this. All right. Swerve can be useful, but you also have to manage how to build them. So for this challenge, I don't know. Have you guys come to a consensus? What would you guys think is the most reasonable in terms of? There's no right answer. I'm just saying. What would you want to do?
H drive thing.
H drive, and then you'd have to have your strategy focusing for it.
Okay.
I would probably do an
Omni wheel.
the
The H or the other one. Holonomic. Okay. Would anyone want to do just a normal tank drive? So for this challenge, it wasn't super important. Like the more mobility, the better. In this case, okay, so that's chassis. Let's look at the points. So on which platform would you want to score?
This one's the highest.
The highest. All right. What's the downside to the highest one?
It's high.
Yeah. So, what would you use?
Just
What would you use to grip the cube? What would you use to lift it to the height?
Well, the other
4-bar?
or elevator.
Elevator?
If it's directly on the ground, it's probably 4-bar.
Yeah, just like an arm.
Arm. Okay, so in this case, 6 feet isn't that high, so you could probably do a 1, depending on the constraints on the thing. You could do a 1-step elevator. A 4-bar would be good because, again, you get that reliable. You always have the thing facing the way you want it, and it's less complicated than an elevator. You could really go either, and it really just depends on the nitty-gritty details of your design, right? How would you grip the cube? How would you grab it in the first place?
Goes out and attaches like
So would you have like something squishy on the arm, and then it just clamps onto it? Yeah. You would use wheels. Would you use wheels?
Yeah, like the compliant
Is the
roller
cube like
wheels.
really squishy? Or like really rubbery?
That's a good question. It is fairly firm. It's not a cinder block, but it's not in the squish.
It's not super slippery, right? So you can get away with not applying a lot of force.
Yeah.
Sideways.
So.
Don't you have one of those?
So, Austin, you said arms, right? So that's a good point. You don't have to use wheels. In this case, if you had, I don't know, if you had some way to control this, and let's just say there's some like foam or something on the side of your arm, and this swivels in and out, right? You drive up to it, it clamps onto the thing. That would work. Wheels would basically do the same thing. It just depends on how do you want to control this. Would you want to use like a piston, for example, to retract it and push it in? Those are the kinds of things you'd want to think of. What I probably wouldn't recommend is using a motor to turn the low arms. In general, you want to get away with using as few motors as possible, just because, like Alex was saying, our battery hooks into this sort of panel that shares the power to a bunch of different mechanisms, and it only has so many number of like ports for motors. So if we just use motors for everything, we would run out. So that's why we want to use pneumatics whenever we can. How would you use wheels? How would you implement like wheels, for example, if you wanted to use compliant wheels instead of like a squishy bar?
You would cycle and would rotate in opposite direction.
And what would you do if you wanted to get it out?
Rotate the other.
So depending on the details of the challenge, you may be able to hold more than one of these, or you may only. Sometimes in the past they've told you you can't have more than one game piece on the robot at a time. Since the game piece is pretty big, I would assume it'd be something similar to that. But yeah, so essentially you'd have a robot that is some type of tank or H or Omni wheel drive. They're all rectangular, they're fairly similar in idea. You'd have an elevator and arm, and you'd have some sort of wheel thing on it, right? And then now we say, okay, you do the chassis, you do the arm, you do the intake, and then we split up. So this is how kickoff goes, essentially. We brainstorm like this. Why would you not want to go for the bottom ones? Yeah, but you can get them faster.
Or you could just like aim for the middle ones and then get them like really fast and also go up.
Yeah, so here's one of the questions where we want to ask, is the extra height worth it? In this case, probably yes, just because the points gap is huge. But one thing you want to keep in mind is, right, is they might be able to say, oh yeah, this one thing, if you do it, is 1,000,000 points. If it's too difficult, then you probably don't want to do it. And because so one of the teams that actually almost was in the final stages of the World Championship this year, one of the teams, Team 346, only did a similar challenge to this. It was similar, right? And they only did like the bottom levels, right? And those don't give you that many points. And then they were able to do it quickly. So it really just depends on what the challenge is. Actually, here, I'll bring up the rules. To continue the discussion.
Should we do the next one? Fields. Okay, so this next challenge.
Actually, one question I have about this is, do the blocks get removed after you put them on?
I was thinking we could have like a large platform where multiple blocks could be placed, but we didn't come up with an exact count.
It's always important to figure out, you know, if you could only fit one block on there, right, then you have to probably do all three, right? But if if the blocks got taken away or you got put into like a slot or something, and you could add.
So if you want to come around back here, view was loosely based on the challenge from 2 years ago. So here's a cube. You're supposed to catch it. Okay, all right. But this was our robot for that challenge. So here you can see some of the things that we did. So what are some things you recognize on the robot? Compliant wheels. Yep. What else? What about the chassis? What do you notice?
Just a standard tank drive.
It is a tank drive. Does anyone know why we'd have omni wheels on the back? So usually when we do a tank drive, we have the center dropped, right? So that way when it turns, right, it turns really quickly. In this case, we didn't have that. So why would omni wheels help with that? Why?
Because of the wheels.
Yeah, the wheels don't have any friction side to side.
So the correct term is wheel scrub. So when you have 6 wheels and you try to turn, the wheels will literally scrub across the ground, right? That's what is preventing wheel scrub.
Mm-hmm. And it worked pretty well. And like in this case, you can see we just have the 4 motors, right? And they're driving each side. This chassis uses belts. Belts across the whole thing. You can see them under there to just connect each side up. In the front here, you can see in more detail the compliant wheels. So what we had in this case were a motor on each side. They spin the wheels in and out. These pulleys on the end are 3D printed. And we use that to grab the cube. Pass. So when closed, so we have pistons out here, right? This is what I was talking about a little bit with the pistons, right? So when the piston is fully retracted, it's open. When it's fully extended, it snaps into place. And that was able to just drive up into the cube. Because the wheels are fairly big here, we didn't have to be super accurate with the motion because it would just sort of suck the cube into the right spot. But yeah, so you guys thought of a robot more or less like this. A lot of teams used an elevator. We did not. And we fixed it a little bit by shooting the cubes instead. It wasn't perfect though. So yeah. So that's what a robot for a similar challenge would look like. Anyone have any questions on the process or anything? Okay, so in this challenge, our game pieces in the cube, it's a disc. The inner diameter of this disc is open and it's 6 inches. And we have to put it on a pole with various various little hooks for them. Let's just pretend that's the thing, and then we have 3 foot, 6 foot, 8 foot. The field, same thing, each driver on either side, and then in the middle, there is one pole for this side, and then there's another pole for the other side. A little bit different. Oh, you load your cubes, same place. Next, actually wait. Pulling a page from the FRC handbook. Your team's loading station is on the enemy team's side. What are some thoughts? What are some things you notice about this game that's different to the last one? Let's start there.
It's a disc.
Yeah, okay, it's a good point. It's a disc.
Anything about the field?
The stuff is in the middle.
Exactly. So how would that be a challenge?
You have to get around it.
Yeah. Right? What else? What about loading? If you want to get more discs onto your robot?
You have to go to the other side.
Right. So what would be a big factor in terms of picking a chassis? Speed. Speed. Traction's a good point because since you're going to cross the enemy side, they may push you around. But also, you want to get as many of these as possible, right? So speed is probably your biggest concern. The heights. What do you notice about the points?
It goes in by increments of 3.
Wow.
Right. Whereas the last one we had a big difference between the top one and the middle one. Now it's not so much, right? So, and the heights aren't that bad either. So, do you think you want to go for the top one or do you want to go for the middle one? Or how do you want to do it?
Just have, like, don't even have an elevator. Just have the mechanism to only set it at the middle one every single time.
It really depends on how many people that's like.
You can hold one at a time, you can place multiple on each hook.
Okay, you know what? I would go for the 9 foot because it would take a, or it depends on how big the field is too.
It's the same.
Same 54 feet. It's like a pretty long sprint distance.
Okay. I would probably go for the 9 foot or the 9 points because it would take a pretty long time to go to get a disc.
Any other ideas? So what chassis would you pick based on that? What kind of drivetrain would you pick?
Really fast.
That could be all.
Yeah, it depends. Depending on what motors and gear ratios you choose, anyone can't be fast. How do you want to do it? You could do an H. Yeah, you could do an H drive, and then you could drive forward, load, go back, and then just move to the side, right? And you don't have to ever turn your chassis. That could be one idea. What else could you use?
Have Omni wheels.
You could use Omni wheels again for the same purpose. What's the problem with the tank drive in this case?
It's not
You can't.
You
So
have
you
to
guys
turn,
turn
turn your entire chassis whenever you want to go here. So if you have, again, just so you can see better, if your robot is here, the front is facing this way. If you had, mechanism, Omni, holonomic, H drive, whatever. You drive forward, you reverse, you move sideways, and you place. And your chassis is facing forward the entire time. So that'd be one of the advantages of those. A swerve drive would also work well. Again, the downside, unrelated to the challenge, is that it's complicated. What kind of mechanism would you design for it to hold the panels?
So the arm goes in the middle and then latches out on the other side.
Any other ideas? That would work. You could make that happen.
How does it look station?
A human player puts a disc in and it's just clipped by itself. The rest you pick it up at a lower height.
I'll grab it from the inside.
So similar to what he said. How would you do that? Would you want to have something that like pushes out, or something that flattens it, or how
Probably push it out.
pushes out? So you would have like 2 bars, for example, and then they push out, and then the friction would keep them in place. Okay.
You could use with wheels.
Yeah. Would wheels be a good idea in this case?
No.
Yeah. It's too thin for wheels. Here, let's add something else. What if the outside of this was covered in Velcro? The outside edge. You would use Velcro. How would you get it off once you held it with Velcro?
I mean, there's a hook, so you could just like use that force.
Yeah, so what Johnny said is that since there's a hook, once you place it on, you can just back off and let the hook hold it in place. So that's a good idea actually. Another thing you could do instead of, so you said have a little arm that pushes out, right? If you had it on the Velcro. Instead of to do that, you could use a piston, for example. Teams have used pistons. So this challenge is based on last year, right? Last year we had the hatch panels. We ended up going for a design that went in and it expanded at the end. But we still wanted it to be pretty pretty strong, so we have like a little accordion thingy that most of you guys have seen, I think. Yeah.
One thing to add to the wheel design, there's one popular design that teams use where they had two sets of wheels that were very close to each other and spinning in opposite directions. So if the panel was like this was like an air hole, it would just come onto there and then get pulled across. So it was very easy to just line up to the center and then it would just get pulled. And then you could just reverse the wheels to push it out.
Do you guys understand that?
It goes inside the hole there.
Yeah. So you use two compliant wheels.
So you have compliant or other flexible.
So it really like relies on the sources for the wheels and design.
Exactly. Yeah. So and they're meant for that.
A lot of the best teams actually ended up going to that method just because it actually worked so well for a lot of teams. It's relatively easy to implement.
9-7 was used the plunger.
Yeah.
So I guess we should talk about that too. You can use suction. Some teams use some sort of suction. It's been done before. You gotta make sure you do it right. They ended up becoming the Einsteins, I think.
Right.
But you know.
Wait,
It's
how do
very
they
easy
get it off?
to not do it right. Some people just like basically shot back
Yeah.
onto there.
Yeah. So
Go on it anyway.
there's a team in our district that like us that put a vacuum in a basket to carry one of the kickballs. It worked right. Not very often, but yeah. So you really want to think about how. You don't want to make it too like janky, I guess, is the moral of the story. You want to go for something as simple as possible. If it's too complicated, there's more things that can go wrong. We want as little to go wrong as possible. That's again, so going back to the arm versus elevator thing, the elevators can get pretty complicated. That's why we went for an arm. So instead of having many little errors, there's just one big one, which is the pulley system. Talk about that later. How would you move your mechanism up and down? If we said, for example, if we said that your robot can't be more than 4 feet high, and the middle one's at 6 feet, and it has to start within a 4-foot configuration, if your robot has to start to match 48 inches tall, how would you extend it?
I'd say an elevator.
Elevator? Like a really small elevator, like a 2-foot elevator.
I
So,
mean, there's also 8 feet. So.
yeah. Because the center of the dish isn't, because it's not very heavy, first of all, it's not very heavy, it's not very big, you might not even need a 4-bar. You could just have like one single arm, and then just move that up to the right height. Especially if the loading station is much lower. So that's something to keep in mind as well.
If you use an elevator here, how many stages do you think you need? If you use like the full height of your
Yeah, if you want to
how many
go to the highest, how many stages do you think you would?
2 or 3.
2. 2 is probably, you could do 3. 2 is probably more likely considering that if you go to 8 feet, you can do 1 that gets you up to 6, and another one that gets up to 8. 3 stages would be that, and probably another thing in the middle. That's just looking for the Good? We have one more. Okay. In this challenge, there are no game pieces. You have to move your robot from one place to another. So just for the sake of the thought experiment, if we're looking at a side view of the field, right? This is where the drivers are. Right? Field. Right, is your enemy drivers, okay? And you start off on the platform. You have to, this is like 1.5 feet, okay? You have to start on the platform, you fall off, and then at the end of the match you have to get back on for more points. Any ideas?
I would use the pneumatic wheels
Why?
so I can sort of like
Okay.
rotation of
Mm-hmm. Any other ideas? On what chassis would you put them? Does everyone agree that you want to use pneumatic wheels for this? Right? Okay, so you can't do an ace drive. You can't do a method drive. You can't do a hollow drive. So what are your options?
Or a sword.
Okay. So you have a tank restore drive. How would you get back up?
Or first, is there any reason to hose worker?
No.
Yeah, okay. You just shoot off, you go down, the squishiness absorbs your thing like through a lot. How would you get back up?
Could you use a 4-bar?
How?
I would look at this right now.
Well, let's ignore that. How would you use it? Let's pretend it's wrong though. Do you want to draw it here at some point? You can, during kickoff, you're gonna have to draw a line. There's no shame, we're all friends here. The only person making fun of you is right there in his mind. Okay.
So like, this is your robot, right? And then this is the platform.
Mm-hmm. This from the top view?
And this is side.
Okay, alright.
Right, and then like let's just say this is just like something that extends, and you have the 4-bar here. You could use this, and like I don't know how you balance it, but you could put this on top of here and just use it to pull yourself.
So that would sort of, so if that pushed it straight down, you would get the front part up. How would you get the back part up?
I think okay.
Well, I mean, it's something you can think about. It's part of the question, right? You can use that, and that'll lift up the front piece of your robot.
Or are you thinking of some way of attaching that part to the platform temporarily? With a suction or gravity? Or is that part of your idea?
So that's a good start. Why don't we just work on this idea, okay? Let's just see what happens. So if this front part lifts the front part of the robot up, it's inclined now. How would you get the back part of the robot up?
And put the arm near the back.
How? How would you put it on? You want to try drawing it up there?
Like just simply add something like here, and then like add, and if you had the arm here, and like it would just kind of like extend and then like
Maybe pushing against the ground?
yeah.
Push it against the ground. Okay. Yes, ma'am?
Could you use like pistons on the bottom of it to push off the ground?
You can use pistons. How would that look on the robot?
There'd be a lot of pistons on the chassis.
How would it be oriented?
You want
Like facing down?
Do you want to put them all over the chassis, or do you want, where do you want to put them?
I don't know how strong the pistons are.
Let's forget about that.
Well, I would put like enough so that it works around, like spread them evenly around the place.
So
Maybe
since
like 2 on the back.
yeah, so since you only have to have the front part up, so this arm is going to easily lift this front bit, so the robot's going to incline, right? You only need pistons on the back, right? So you can put a couple pistons here, right? They have to be pretty big. That's the point when they push down. Okay, so let's pretend the robot is this is the ground. Okay, let's just say that your robot is up in the air. The piston is touching the ground. Okay? Now what? No. No. Because they've been on the team and they know the answer to this particular question.
You know,
Yeah, there's many ways to do this. This is just one of the ways to do it.
Okay. Never mind.
You can say it after. Yeah,
after a couple of
Yeah. Need it?
You can have wheels at the bottom of the pistons on the arm.
All right. And then what?
You need probably the one on the arm forward.
So where would you put your motors? Which wheels would be driving?
The ones on top.
So the ones on the arm. So you have a motor here.
And then you drive forward and you lift up the pistons.
Does everyone see how that works? You can see how that works? So basically, two-stage system. The arms lift up, pistons push up back. The wheels here are simply there so they can roll. They don't actually do anything. And the motor would go on the arm because the motor on the end of a piston is not a very good idea, just because of the lack of space. And then you just drive forward. We ended up doing something sort of similar to this. What are some other ways you can do the same thing?
For example, moving on top of the platform.
Yeah. So this is one valid way to do it. You can do something similar to this. Instead of doing this, you can do any different type of arm, but the idea is the same. Lift up the front, lift up the back, and then you just drive on it, right? It works pretty well. What are some other? Anyone think of any other ideas to do it? Richard, do you want to do something crazy one, or do you want to?
Maybe some
Do you want to pull up Roblox or someone? Okay, let's think of some other ways in the meantime. So, how could we use, instead of having the arm in the front, could we use 4 pistons on each corner? How would you drive it then if you can't have motors on pistons? So one thing to say with this design is that this design works pretty well, and then once the chassis wheels touch the platform, once it goes that far, then these can just drive, right? Okay, so knowing that, how do you get 4 pistons to work?
Oh,
How so? Yeah.
So these two would be shorter than this one, so we could like move it forward. Essentially, I think this.
That's
Okay. So like
you triple game if you can.
this would be in the.
oh yeah.
In the. So it would begin down here, and you would push it up so this could move a little bit forward, and then.
So you're onto something. The one problem that I see with this is that this one going straight down would completely counteract this one going diagonally up. Right? So if this was going down, so I want to go down, this is going up, it'll make it difficult. So how would you want to do it? Anyone have any ideas? If you want to have a piston at an angle or something pushing diagonally, how would you get it to work? So instead of having one go down and one go diagonally, if you have them both go diagonally, just in front, right? How would this work then?
You would tip over that way.
It would. So how would you fix that?
Front this in more forwards, so that you on ladder sits and have to shield.
Yeah. Yes, you could do that. You could be turned back wide or longer, you mean?
Yeah.
You can, well, yeah. So you make it slightly longer. You would have to drive up a little bit more, and you have to practice, of course. But you can have it so that once you extend, right, then your robot just sort of falls onto the platform. You just return to distance. Another way that teams have gotten it to work is by flipping over onto the platform. And because it's at the end of the match, right? At the end of the match, you climb, and it doesn't matter what happens next. You have to come back off. Okay, cool. So this is from. Okay, yeah, this is the robot. Okay, so yeah, so
Yeah, this robot right here.
what's the middle one?
Did you say that that was the team that made it to the world?
Yeah. So they were captains of one of the top 8 alliances in the world with that robot design. So do you see what they did? They just had an arm, lifted the whole robot to the point that when they fell, they would fall into the platform, and then they'd be good.
I found a couple other cool videos just for like inspiration. This one uses suction, so it uses a suction cup and uses like a motor to form a vacuum against the platform. That's just you just look straight up. This one also has
This is my
interesting
favorite.
approach. Where it like tilted to 45 degrees and then launched itself.
Was it the one that
perfect.
fell over? Okay. Was it Triple Helix the one that fell over?
Once.
I think they fell over once. Our first competition.
Okay, wait, you showing that one? Here, actually, let's replay that and study that a little bit more.
That's kind of like
Yeah, so pause. So, what they have going on is they're angling the robot, right? And they have the robot as a trajectory that once they fall, they'll be on the platform. So they thought really carefully about this. We were considering doing something similar, but they decided that it was too risky.
And they know that they're only going to tip once they reach a certain point where when they tip, they're going to be able to platform and be able to drive on.
Yeah, so if you play, then they fall onto the thing. The downside to that design is that they can only fall into the third step. Does anyone know why? They can only fall into the top one. Why can't they fall into the lower one, to the middle one?
Because their like robot only falls over after a certain distance of.
Well, they can still extend and then fall into the second platform. Why did they have to fall on the top one? Why can't they do the second one?
because the metal part that supports that first point, they will probably fall.
That might happen, but also it's too much of a height for it to drop. If it's designed to only fall a little bit to the third platform, if it does the same thing, falls to the lower platform, then they'll actually take damage, and that would not be good.
One more just for like inspiration that we do a little more consideration.
Yeah. Okay. Yeah. So in this case, this middle robot is holding up 2 other robots, and they're all climbing together. And so that gave you a heck ton of points, and it was you see it a lot at the higher levels, of course, because it's not something easy to pull off. The way they do it, really simple. Just have like big platforms, like little wings. You know?
So they get the points for all 3 robots?
They get the points for all 3 robots. So in this particular challenge, climbing, if you didn't climb at all, it was 3 points at the end of the match. If you climbed to this first low step, it was 6 points, and the top one was 12 points, and so this would give you 36 points, which is crazy. Especially when the average like match score was like 60-ish. Your average match was 60. 36 is a lot. So yeah. I mean, our time's almost up. Well, I mean, it is up. But quickly before you guys go, thanks for coming. But also, hopefully, out of what we did today, hopefully you can take away how we analyze a game, the thing we think about, and how different sort of teams, how multiple things can achieve the same goal. You don't have to narrow down and say this is the way it must be done. There are a lot of ways to do it, but it also really depends on the points and the rules and all the other things.